Okay, in this lecture what we're going to do is we've got one more example of equivalence relations, and then we are looking at, we'll just do a run through of chapter 1 summary. Okay, so here what we have is equivalence classes. Equivalence class of 1 is 1, 3, 5. Equivalence class of 2 is 2, 4. And equivalence class of 6 is just 6. And the equivalence classes of a relation. Now, if they're equivalence classes, this defines an equivalence relation. Write out the set or in terms of ordered pairs. Draw a graph that represents this. I think we're going to draw 4 diagrams, the best one being the digraph. Okay, so we can say that everything in the equivalence classes relate to everything else. That's like what we said about you can do the Cartesian product of this with itself, this with itself, this with itself, and form it like that. Okay, so the relation works like this. So everything in the equivalence class is related to everything else in there. And that's the same as forming the Cartesian product, really. So 1 is related to 1, 3, and 5. So 1 is related to 1. 1 is related to 3. And 1 is related to 5. Okay, 3 is related to everything in there. So 3 is related to 1. 3 is related to 3. And 3 is related to 5. Okay, and 5 is related to 1, 3, and 5. So 5 is related to 1. 5 is related to 3. And 5 is related to 5. So this is similar to what we did in the previous thing. Then everything in here is related to itself, and nothing in here is related to anything in there, and nothing in here is related to anything in there. So we have 2 is related to 2 and 4, so let's write that. 2 is related to 2, 2 is related to 4, and then 4 is related to everything in there. So we've got 4 is related to 2, and 4 is related to 4. And if you do this, by the way, you're guaranteed what you have is an equivalence relation, and we'll explain maybe briefly why. And finally, 6 is related to 6. So this is definitely an equivalence relation because, let's see, because everything in a block is related to everything else, it's going to be symmetric. So if you take 3 and 5, 3 will be related to 5, 5 will also be related to 3, because 3 and 5, 3 is related to everything, 5 is related to everything. It's going to be reflexive for the same reason, because everything in a block, so every node is going to have a loop, everything is related to everything else, in particular to itself. And the transitive is probably a bit harder, but how would it work? Say if you take, say 1 is related to 3 and 3 is related to 5, so that's 2 relations, then because everything in the block is related to everything else, you're automatically going to have the 1 to the 5. Yeah. So that's what we see here. We see 1 to 3, see 3 to 5, but because everything in here is related to everything else, you're going to have 1 to 5 in there as well. So it's transitive. Okay, so that's how we do that. Now, what we're going to do now is we're going to draw the graph. Now, I strongly actually recommend the digraph, but it's just nice to see these other things. So let's do a coordinate graph. So 1, 1. Now you don't join the dots in these because there's only finitely many points. When you join the dots, that's infinitely many points. So 1 is related to 1, 1 is related to 3. So that's 1 along the x, 3 along the y, and 1 is related to 5. We have also 3 is related to 1, 3 is related to 3, 3 is related to 5. And finally, 5 is related to 1, 5 is related to 3, 5 is related to 5. We also have 2 is related to 2, 2 is related to 4, 4 is related to 2, and 4 is related to 4. And finally, we have 6 is related to 6. So the pattern, as I said, is hard to block, but you have these rectangles. So you see the blue rectangle is the first bit, the black rectangle is the second bit, and the green, it's just a trivial rectangle, it's got no area or anything, is the last thing. And this is saying that if you do the Cartesian product of each block with itself and union them, that means kind of, you know, so all of these, all of these, all of these, you get it. And now, strictly speaking, as written, you'll get repetition, but of course if you've repetition in a set, so let's just write this, if you've got the set containing 2, 2, and 3 sets, everything is distinct, so this is actually the set containing 2 and 3. Okay, so that's one way of doing it, coordinate graph, not recommended, but just a nice picture. Arrow diagram, I can do it if I write it in this particular order. It's nastier, it doesn't tell us much, but let's see. So this is the set A, and I'm saying I want to write in there 1, 3, 5. So let's keep the colors going. 2, 4, and finally 6. 2, 4, 2, 4, and finally what have we got? 5, 3, 1, 1, 3, 5. So we the arrow diagram, if you recall, things that are related, you join them up. So if we look at it, everything in the blue is related to everything in the blue. So 1 is related to 1. So this is not a digraph, this is an arrow diagram. I don't recommend this, so I'm just going to show it to you. There's lots of options. When we analyze later functions, we'll be recommending the use of arrow diagrams. But for relations, really, the best job is to use digraphs. Okay. Like this doesn't actually tell you much. Now the only thing is that the way we've written it in the blocks, you can actually see that it's an equivalence relation because you've got this partition. It's nasty though overall. The digraph is the king. So the digraph says 1, 3, 5, 2, 4, 6. And things that are related, you draw arrows between them. Now we can go back and do this, but of course it's just understanding that these are equivalence classes. This is 1, this one, this one. Everything here is related to itself. So 1 is related to 1, 1 is related to 5, 1 is related to 3. 3 is related to 1, double edge. 3 is related to 3, 3 is related to 5. Finally, 5 is related to itself. It's also related to 1, it's also related to 3. And then in here you have 2 is related to itself. It's related to 4. 4 is related to 2, and 4 is related to itself. And finally 6 is related to itself. And look, you don't have any kind of interactions between them. So these are equivalence classes. And then the final example would be that represents a partition diagram. So we might go with something like 1, 2, 4, 6, 3, 5. Now this isn't really standard, but it just kind of shows what we're doing. And I've forgot to use the colors anyway. So you partition it. So you write as a couple of subsets that if you union them, you get the original set. What do we call the set? A. And there's no intersection between them. Okay. So actually a good example of an equivalence relation, and it's something that probably needed in the previous chapter, is value. So things can be different but have the same value, they're somehow equivalent. And this is, I suppose, in a certain sense, the whole basis of money. Like say, if you think about maybe 10 euros phone credit, 10 euros of potatoes, 10 euros of tea, and 10 euros. So you can put them all into the one equivalence class, and you represent that equivalence class with a tenor. And they're all kind of equivalent to a tenor, this is the idea. So for example, let S be the set of all objects in a shop, and suppose you're only allowed to purchase one of each object. Then the set of shopping trolleys would be subsets, so you can just take one of each thing. We can define a symmetric relation on X. So X is basically all the possible shopping trolleys. If you take only one or no, you can't grab 2 bags of potatoes, just 1 bag of potatoes. But you could grab also, whatever, bag of meanies as well, as long as you don't have exactly the same item. But these trolleys. So 2 shopping trolleys are related if their euro value is equal. So this is an equivalence relation because every trolley has the same value as itself. If trolley A is the same value as trolley B, then trolley B is the same value as trolley A. And if trolley A is the same value as trolley B, trolley B is the same value trolley C, say 62 euros, then trolley A is also related to trolley C, so that's transitive. Similarly, you can say the two sums of cash, any currency, are related if they both convert to the same amount in euros. So that's why it's kind of equal. So whatever it is, €1 is, we don't actually, it's not the same thing as say £1 and 10 pence sterling, but we say they're equal, they're kind of equivalent. So this is why we call them equivalence relation. Okay, so that's everything on equivalence relations. There's some exercises there. We'll go briefly through a little chapter summary. My recommendation is that you kind of aim to understand everything on this, because we will be building upon this later on in the book, in this module, and also in your maths next semester. Okay, so a set is a well-defined collection of distinct objects, and order is not important. So the distinct object means the set containing A and A is just the set containing A. You don't have duplication, and order is not important. The set containing A and B is the same as the set containing B and A. An object X is in a set, or you say it's in a set, a member set, or element set. You write it as X in A. This symbol means in. The cardinality is just, if it's a finite set, is a fancy word for the number of elements, and you use these bars to indicate this. A subset B of a set, B subset A, or subset equal, is a set such that every element of B is an element of A. It can be thought of a selection of some of the elements of A. So sometimes this means that it's a strict subset, but to emphasize, you might write that. The power sets of this thing, you need to know what that notation means, is all the subsets of A. Its cardinality, so the number of subsets, is 2 to the power of the number of elements in A. The union of two sets A and B is a set consisting of those that belong to A or B or both. So I would say it's all those elements that belong to A or B or both. If you want to list A union B, my recommendation is list all the elements of A and then all the elements of B that you haven't got yet. The intersection of A and B, denoted A intersection B, is set consisting of all those elements that belong to both. So I think this is something I ran with before. Union is like all, and intersection is like both. Inclusion, exclusion says number of elements in A or B is number of elements in A plus number of elements in B minus number of elements in A and B, because you double count the number of elements in A and B here and here. The empty set, written with this symbol or this, is set with no elements. Now what you don't write is this. This is incorrect. I'll mark this as wrong. The way you want to think about a set is, or a way of thinking about a set is kind of think of a plastic bag of objects. And the empty set is like a plastic bag with nothing in it. And this is a symbol for this. This is a symbol for this. So this thing is same as this. This is a plastic bag with nothing in it. This, in fact, is a plastic bag with something in it. Another plastic bag. It's like a plastic bag inside another plastic bag. It's not empty. And you might say, oh, there's nothing in it. Well, there is. The plastic bag is in the plastic bag, not empty. The difference of two sets, or the relative complement, consists of all those elements that are in A and not B. So this we might write down is the same as A and not B. So what do we got here? Yeah, so this is all the things that are, okay, that's okay. The Cartesian product, this A times B, consists of a set of all ordered pairs that you can form where the first thing is in A and the second is B. The order here is important. And because order is not important for sets, use curly brackets, but when order is important, use the rounded brackets. Okay. A relation between two sets A and B is a subset of this, so it's just some ordered pairs. A relation on A is a relation between A and itself, so it's a subset of A times A, so it's some ordered pairs, first thing in A, second thing in A, best studied with a digraph. A relation is reflexive if everything is related to itself, so it's written A is for all elements in the thing, either everything is, well, that is not either, everything is related to itself, which can be written like this. in terms of the digraph, if all nodes in the digraph have loops. All, not some, all. If there is a node without a loop, then the relation is not reflexive. And you say it's not reflexive because that node has no loop. Relation R is symmetric if whenever A is related to B, we also have B is related to A in terms of digraph if all edges in the digraph are double edges. And then the harder one, the transitive, a relation R is transitive if A is related to B and B is related to C, we also have A is related to C. And it's about shortcuts in terms of shortcuts. The digraph. If nodes connect in two steps, so say A to B, B to C, that A to B, B to C, you can also go in one step. So shortcuts are triangles. A relation R that is reflexive, symmetric, and transitive is said to be an equivalence relation. And finally, if you have and this has to be an equivalence relation, because it doesn't make sense to talk about equivalence classes for something that isn't an equivalence relation. The equivalence class of A is a set of elements related to A. So you just take all the things that are related to A. We've best seen an example. Okay, so that's chapter 1 done. And I think we're going to leave that for week 3 because you probably need to do a lot of exercises. And we'll go and look at chapter 2, most of chapter 2 next week.